What's up, scholars? Today we're talking about proving statements about segments. Let's remind ourselves of a couple definitions. What is a theorem? Well, it's a true statement that's a logical conclusion based off of other true statements. A true statement that logically follows other true statements. So if we accept these other true statements, we have to accept the theorem that's a true statement based off of those true statements. It's just truth. That's what it is. We can prove things using a two-column proof, in which we have two columns that have statements and reasons, and every statement we make has an accompanying reason. Every one. So we don't ever say something without saying why we're saying that thing. That's a two-column proof. It's a way of organizing your statements and reasons. You could also do a paragraph proof, which would be writing out your statements and reasons in full sentences. Writing statements and reasons in full sentences using all your grammatical prowess. Cool. All right, let's remind ourselves some segment properties of congruence. For instance, the reflexive property said something was congruent to itself. So segment AB is going to be congruent to itself. The symmetric property said that if we have two segments that are congruent to each other, like segment AB is congruent to segment CD, then if we need to, we can flip the order around and it's still true. Then segment CD is still congruent to segment AB. And then my personal favorite, the transitive property. If we have two segments that are congruent to each other, like AB is congruent to a segment CD, and that second segment is congruent to another segment, CD is congruent to EF, then the original segment, since it was congruent to something that was congruent to something else, must be congruent to that something else. We can skip the middleman CD and say AB is congruent to EF. AB is congruent to EF. Cool. One other thing I want us to remind ourselves about is the definition of congruence. And I'm going to abbreviate as defin of congruence. That says if something is congruent, let's say segment AB is congruent to CD. If two segments are congruent, then their measures are equal. So AB is equal to, sorry, don't put the bar on top. If we're talking about measures, we don't put the bar on top. So if AB is congruent to CD, then their measures are equal. AB equals CD. That means their measures are equal. That's by the definition of congruence. And the reverse is also by definition of congruence. The converse is also true by definition of congruence. If segment AB equals segment CD, meaning their measures are the same, then the segments themselves are congruent. So, if we are ever trying to say that congruent segments are equal in measure, our reason is going to be definition of congruence. If we are ever trying to say that segments have the same measure, So those segments are congruent. The reason will be definition of congruence. Okay, let's put that into place, put that in plan, and example number 1. That's off screen. All right, example number 1. Prove the symmetric property of segment congruence, which was this property here. If AB is congruent to CD, then CD is congruent to AB. We're going to prove that is true. Why is that true? Well, let's see here. We are given that segment PQ is congruent to segment XY. We are going to try to prove that segment XY is congruent to segment PQ. So, our first statement is the thing that we're given, which will always be true. And they give us a little hint here. We're going to use the definition of congruency in our next statement. So if segments are congruent, then their measures are equal by the definition of congruence. So if these segments are congruent, then their measures are equal by the definition of congruence. Now we really want these to be in the opposite order. All right, that's what we're trying to prove, that segment XY is congruent to segment PQ. So we need these to be in the opposite order. Why is it true that XY equals PQ? Let's think back to our properties of segment equality now. Yeah, it's the symmetric property of equality. Symmetric property of equality, which is different than the symmetric property of congruence, because one's for things that are equal and one's for things that are congruent. Now we got them in the right order. Awesome. So we can say that since these segments are equal, their measures are equal, then those segments are congruent to each other. Segment XY is congruent to segment PQ by, what's that reason? Why do we get to say this? It's the definition of congruence, which from here on out I will always abbreviate like this, because I'm a math magician. I want to write as little as possible. There's our definition of congruence. Beautiful. Nicely done. Okay, let's keep cruising. Okay, let's look at example number 2. In the figure below, prove that segment EG is congruent to segment FH if we are given that EF is equal to GH. So we're trying to show that this segment EG is congruent to segment FH, given that we know these tail ends have the same measure. Now let's think about this for a second. What do we see is similar about these two segments? We've got segment EG and segment FH. I can see that they overlap here. They have a part that is the same here. And they have end pieces that are equal to each other. So they have a part that's the same. Sorry, they have a part that they share, right? This segment FG is shared between the both of them, and then their ends are equal to each other. So if they have equal ends and they share something that's equal, they must be equal. They've got equal ends here. They share something that's equal. So we add these equal ends to something that's shared. Equal plus equal means something that's equal. That's going to be our general idea here. So we are given that EF equals GH. That is given. First reason, always given. You will always be given something, so you're always going to get 1 point. Because you'll always be able to fill out that very first thing. Always, always, always. All right. For a while, we're going to do proofs where everything's, or not everything, a lot of things are filled in for you to kind of practice this proof process. So, let's look at step 2. Says EF plus FG equals GH plus FG. How does this statement relate to this statement? EF plus GH equals, or EF equals GH. How does that relate to EF plus FG equals GH plus FG? I think we added FG to both sides. So that is the addition property. We added something to both sides. Addition property of equality. We added something to both sides. Namely, we added FG, which is that part that they share, right? Step 3, EG. EG is equal to EF plus FG, and FH is equal to GH plus FG. Why are these things true? Why is EG equal to EF plus FG? Let me cover that up so we can look at it. Why is EG equal to EF plus FG? Why is a long segment equal to 2 smaller segments added up? Oh yes, the segment addition postulate. Segment addition. Postulate. Postulate. That one's going to show up all over the place. It's very popular. Very, very popular. Okay, cool. So, they're giving us another hint. Reason number 4 says substitution property of equality. We're going to try to find some place to substitute something. So we need to find something that's equal in 2 different equations. Oh, like EF plus FG, that's up there. EF plus FG is up there, so I could take this thing and plug it in for EF plus FG because they're equal to each other. And GH plus FG, that's right here. So I can take this FH, what is equal to GH plus FG, and plug that in right here. So instead of EF plus FG, I'm going to plug in EG equals, instead of GH plus FG, I'm going to plug in FH. That's by substitution. We did some plugging in. What were we trying to prove? Oh, that those segments were congruent. We have that they're equal to each other. So this one's simple. EG is congruent to FH. If something's equal, then it's congruent. That's the definition of congruence. Great. You guys are doing wonderful. Thanks for hanging in there. Let's do example 3 together. Complete the proof. We are given that RT is congruent to WY, so these big segments are congruent to each other. We are also given that ST is equal to WX. They have the same measure. So we have 2 givens that are written for us in here. So sometimes you don't write all your givens at the beginning if you're not going to use them all as part of your proof. It would not be wrong to write them all at the beginning, but you can split them up. So let's work through this partially completed proof to try to show that segment RS is congruent to segment XY. Okay, so we're starting out with segment RT is congruent to segment WY. Why is it true that those segments are equal to each other if they're congruent? That's the definition of congruence again. Of congruence. Great. And they tell us RT is equal to RS plus ST. RT is equal to RS plus ST. And WY is equal to WX plus XY. Why is that true? Why do two segments add up to make a third big segment? Oh, it's the segment addition postulate! Segment addition postulate. Okay, got it. So then why is RS plus ST equal to WX plus XY? Well, I see WX plus XY over here. And that's equal to WY, which is up here. And RS plus ST is here, which is equal to RT, which is up here. Oh, so they substituted. Instead of RT equals WY, they put that RS plus ST in here because those are equal. And WX plus XY up here because those are equal. So we did some substitution. Cool. Great. Now we're going to use our other given. ST equals WX. That is given. And then we got another little hint here saying we're going to do some substitution. What are we going to substitute? Well, let's look at this equation and this equation. So looking at 4 and 5. We're trying to get down to RS is congruent to XY. So we're going to need to get to RS equals XY first, and then they'll be congruent by definition of congruence. So we have RS plus ST equals WX plus XY. And ST equals WX. We're trying to get RS to equal XY. Oh, I see. Let's plug WX in here, since it equals ST, so anywhere I see ST, I can plug in WX. So we'll get RS plus WX equals W plus XY by substitution. And then we're almost here. We just need to subtract off that WX to get RS equals XY. Subtraction. The subtraction property of equality. Great. Now we have RS is equal to XY, and we wanted RS is congruent to SY. And that's the definition of congruence, baby. That's it. Okay, cool. You made it. You did a wonderful job. Thanks for hanging in there. Stick with me for some more episodes of Math with Ms. Akin. I love you, scholars. Keep on the hustle. I'll see you next time.